I already read through the chapter on Intro to Mathematical Cryptography, and yes, I'll make sure to do my intro as well. I'm Chloe Lewis, co-founder of the Marma J Foundation, lead of Marma J Labs, and just kind of working to support education, cryptography education specifically at the moment. And so to do that, I am engaging in the Uncloak Cryptography Engineering Study Group. That's what I have over here on the right hand side of my screen. We're at session 10, week 10. And we're kind of getting into the math behind cryptography now. We did a lot of theory and get kind of a lot of like how pieces fit together over the past kind of 8-9 weeks. Week 9 kind of started getting into the math side of things from a high level, and now we're kind of digging a lot deeper, I would say, actually. So there's a few exercises at the end, and I'll kind of go through those first to kind of shape the context of what we're doing and why we're doing it potentially. If anyone does happen along this video and you're like, what the heck's going on, you can just go to the link in the description and just go to the exercises. And maybe you're better at math than me and you can just go straight to it. Please don't sit here and watch my stream. Just go straight to the link. Also, Thor does stream this content on the Uncloak YouTube channel. So please just go through the channel, watch or listen to that stream, and kind of you can go through the content yourself. This is just me going through it so I can take some notes on the left hand side here and keep myself accountable to my educational journey, I guess, my research journey. So we know already we're going to look for something on page 19. So this is kind of, again, what the notes are for me. I'm kind of switching up my note taking a lot. That'll probably be very evident as I go through this. I used to do a lot of copying and pasting and a lot of kind of just rewording things to go back through it later more efficiently. And now I realize I don't have time to go back through anything, and so I just kind of need notes to just help me kind of answer a question or solve a problem or be able to kind of go back through like a month later and still know what's going on. So anyways, for now, page 19, implement the modular fast powering algorithm for big ints. So looks like I'm gonna have to worry about the modular fast powering algorithm. Let's just put it up there, why not? It's not that many things. For a positive a and b, which are real numbers, suppose that there exists a u and a v that satisfies e plus bv equals 1. And this always, I read it, I understand it, but honestly I'm just gonna put this here because I get what it's talking about already. Doing some proving GCD is actually 1. There's some like algorithm that you can actually use, and so obviously it's saying, hey, implement this algorithm. If you can go to the solutions and see how it's done as well. Next question, suppose that g to the a is congruent to 1 mod m and g to the b is congruent to 1 mod m. Prove. Ooh, this is a good one. Proofs are hard for me, like very, 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 very non-intuitive for me, like just absolutely complete, like just, yeah, not intuitive for me. But I go through them like dozens of times and I still barely get them, but I'm starting to somewhat get them, at least with cryptography, because I understand why they're useful. And that's kind of why I like the math side of things. So using a program, so this is actually the hardest part for me so far. A lot of modular, particularly the intro parts of it, I'm starting to understand how it starts to fit together and what pieces are important. But the whole like something's a generative of a group if it goes through every number of a group without repeating. But obtaining a generator is like the hard part for me. Like, I get what a generator is, but then actually figuring out how to use it or how to find it is tough. Both values are prime. So it's saying like, I guess this value is prime and this value is prime, and you're trying to find a generator that can generate over both of these. So how did you do it? And there's obviously a program for finding generators, or like taking two values and finding their GCD and then maybe that would be the way to do it, right? Take 2 primes and then find the GCD, and maybe that would give you the generator. I did have some code from last. It was silly through the first one, but I just wanted to get it in. Okay. Second, try to understand the crux of each algorithm, theorem, lemma, and proposition, and summarizing in a sentence for your reference. For instance, the fundamental theorem of arithmetic? Yeah, that says arithmetic. I just can't read today. It states that if n is greater than 1 and is a real number, then n may be factored into the product of primes. That is, for all n greater than 1 a real number, there exists a unique factorization p of I and e of I such that n is, for the product of all pi, that's one of a ei, the greatest common denominator. And this is where I'm gonna have problems. Sometimes reading these out, like, I have to sit there for a second and like be like, what are you trying to say again? The greatest common denominator of a and b minus set of 0, maybe less restated, GCD of a and b equals the product, all the products of I for p min. Okay, that, I don't know what min is there for. EI, A, EI, B. Where is A and B coming from? I'm not good with proofs though. So 5, try to understand the proofs, but don't fret if they don't come naturally to you. Proofs often reveal not only the reasoning behind the theorem, but even motivation to further theorems and corollaries. My gosh. However, proofs are often the hardest part of reading mathematical text. I will concur, I will attest to that. Only spend as much time as necessary learning proofs. You decide what necessary means. Okay, so I'm gonna spend maybe 2 to 5 minutes on each proof. Longer than that on my own, but not on the stream. The goal of this week is to give a more complete introduction to mathematical tools using public key cryptography. Pay most attention to sections 1.2 to 1.5. More interesting, and therefore the book is focusing on that. Good thing too, because now, almost 20 years later, pretty much only public key crypto is used for the most part. In my understanding, again, I could be wrong. I'm sure private key crypto is used in many aspects, but in the blockchain space, at least what I'm most used to, it's a lot of public key crypto. Modern mathematics, I guess not for hashing and stuff. I guess that's still private. Anyways. As Julius Caesar surveys the unfolding battle from his hilltop outpost, an exhausted and disheveled courier bursts into his presence and hands him a sheet of parchment containing gibberish, a bunch of gibberish. Within moments, Julius sends an order for a reserve unit of charioteers to speed around the left flank and exploit a momentary gap in the opponent's formation. How did this string of seemingly random letters convey such important information? The trick is easy. Once it is explained, simply take each letter in the message and shift it 5 letters up the alphabet. Thus, J in the ciphertext becomes E in the plaintext, because E is followed in the alphabet by F, G, H, I, J. Applying this procedure to the entire ciphertext yields enemy falling back, breakthrough imminent Lucius. The second line is the deciphered plaintext, and breaking into the words and supplying the appropriate punctuation. So, cryptanalysis of simple substitution ciphers. So here's the actual fun part, in my opinion. So we know about the cipher. Now we're going to talk about actually breaking the cipher, which typically is where I enjoy spending my time. I'm definitely not. Anyways, how many different simple substitution ciphers exist? We can count them by enumerating the possible ciphertext values for each plaintext letter. First, we assign the plaintext letter to one of the 26 possible ciphertext letters, A to Z. So there are 26 possibilities for the plaintext A. Next, we are not allowed to assign B to the same letter as A. We may assign B to any of the other remaining 25 ciphertext letters. So there are 26 times 25 equals 650 possible ways to assign A and B. We have now used up 2 of the ciphertext letters, so we may assign C to any of the remaining 24 ciphertext letters, and so on. Thus, the total number of ways to assign the 26 plaintext letters to the 26 ciphertext letters using each ciphertext letter only once is 26 times 25 times 24, all the way down to get to Z, which is the 1, so 26 factorial, which is this huge number over here, which seems huge, right? It's not that big though. It's only 10 to the 26. So there are 10 to the 26 different simple substitution ciphers. Each associated encryption table is known as a key. So this entire table, right, is known as your key. Your encryption key, your decryption key. Suppose that Eve intercepts one of Bob's messages and that she attempts to decrypt it by trying every possible substitution cipher. The process of decrypting a message without knowing the underlying key is called cryptanalysis. And I'm not going to write definition this time, even though I kind of want to, but that just takes very long. Not that long, but longer than just